Awesome. So there are a couple of things I want you to kind of highlight here. So here in this prime function, which we wrote in the last class, so there is a main function. There are three functions. There is is prime function. There is readn function. So these are three functions. So what happens is when you start executing the program, so every function, if you see, every function, it can be either active or inactive. So and then there can be multiple activations of the same function that we will see in maybe in Saturday's class. So first idea is a function can be active or inactive. Like for example, when we are executing the main function is active, right? Uh, and let's say if you are at, let's say on when we are at line 40, the only function that is active, so before till line 40, the only function that is active is main. So here if you see, the only function that is active is main. And on line 41, we call the readn function. So main calls uh, readn function. For the sake of simplicity, today in today's class, I want to say, give a simplistic picture that every function will have some chunk of memory allocated in the RAM. This is the place where it stores its local variables. This is the place, and like similarly, readn also has a chunk of memory allocated in the RAM, and this is where it allocates memory for the local variables. So when main calls readn, there are two active functions. Main is active and simultaneously readn is also active. And then after we come out of readn, and then so when readn becomes active, the memory that is associated with readn, it will be available to it. Okay, it will be allocated to it. So and after we come out of after line 41, so readn will no longer be active. And then when we come to line 43 and when we call is prime, so what happens is now no, so is prime main and is prime will become active. It is possible that there can be multiple active versions of the same function. That is where the idea of recursion comes into picture. And the idea of recursion we will study in the Saturday class. So let me give a slightly better picture. So if you take the memory, so like when you give, when you execute a program, so this is your whole, so the whole memory. This is the RAM. There is a processor, there is RAM. This is your RAM or main memory. And then you have so what is your memory? How do you view our memory? How do we view our memory? Can someone tell me what is the logical view of our memory? Yeah, it's a linear array of bytes, continuous sequence of bytes. Good. Our memory is looked at and every byte has an address. Every byte has an address. So every byte, every byte has an address. So if you take a program and when you execute the program, this is our whole memory. Let's say our memory size of our memory is 4 GB. 4 GB is something like 2 power 30, 2 power 30 bytes. 2 power 30 bytes is 4 GB. Is equal to 4 GB. Let's say this is the size of our memory. So if we start addressing no, the memory, and if you kind of say this is the address 0, the address of this will be 2 power 30 minus 1. 2 power 30 minus 1. All right. So our whole memory, it's a sequence of bytes. It's a linear array of bytes, and every byte has an address. And every byte has an address. So what happens is when you compile your compiled program is residing on the hard disk. Your compiled program is residing on the hard disk. And when you give the program for execution, the program takes the program will be allocated, will be loaded from the hard disk to the memory. Will be loaded from the hard disk to the memory. And then, so if you look at, this is what is called as a main memory layout of a program. So what happens is when you give a program for execution, after you give, program is an inactive entity, it is present on the hard disk. After you give a program for execution, it becomes what is called as a process. It becomes an active process. Like for example, like Chrome icon is there and Chrome executable file is there on your system. If you want to, if you double click it, then from the executable file that is present on the system, a process gets created. A Chrome process gets created. So every process has a main memory layout. Every process has a main memory layout. If you look at the main memory layout of a process, so there will be a chunk of memory which is allocated to the operating system or a kernel. And there will be something, and if you see the lower side of the memory, many times you have what is called as a BIOS present, basic basic. So this is usually your BIOS will be present in ROM or flash RAM. So BIOS will be, so whereas all of this is usually volatile RAM. So BIOS will be present in earlier days it used to be present in ROM, but nowadays it is present in flash RAM. Flash RAM is modifiable. It takes the right time for flash RAM is more, but it is modifiable. Um And then you have what is called as a text section. This is the place where the instructions of your program are present. And then you will see there is what is called as a data section. So this data section, it is this is the place memory for global variables will be allocated. We will see what global variables are in a while. And then there is what is called as a heap. So we will study again later what heap memory is. And then there is what is called as a stack. So the memory, it grows from the stack. Stack is something, you can push something onto the stack. You can push some number onto the stack, or you can push some data onto the stack. When you push some data onto the stack grows. And when you pop something from the stack shrinks. That is what happens. And the memory for the local variables, they will be allocated in the stack. The memory, like for example, the memory for the variables I and n will be allocated on the stack. So the memory for local variables will be allocated on the stack. The memory for the global variables, so on the stack, local variables, memory for local variables will be allocated. And on the in the data section, memory for global variables will be allocated. So one idea here is this is what is called as a memory layout of a process memory layout. But if you see on your system, on your system, so there are multiple processes running, right? So do you think, let's say on your system 4 GB memory is available, do you think the whole of the 4 GB memory is allocated to a process that you are running? Do you understand the question? On your machine, there is 4 GB RAM that is available. So, but there are at the same time, like for example, on my machine, you can see I am running Visual Studio Code, I am running Zoom, and I am running some PDF file. I'm running a PDF reader. So there are multiple applications that are open now. How is it possible that each of these applications will get the whole of the memory for itself? How is it possible? So you will understand, you will read about this idea later, but I will give a kind of glimpse into this, which will make many ideas clear for you if you look at it at the right abstraction level. So the address space that a process gets, the address space that a process gets is what is called as a virtual memory layout. This is every process. So let's say this is virtual memory layout, virtual memory layout. So this could be for Chrome, and there can be another, this is, let's say, VS Code process. I use VM for shorthand, virtual memory layout. And then, so this is not real memory, and then there is a real physical memory present in between. So real physical memory. So what happens is, so your virtual memory is divided into what are called as pages. Is divided into what are called as pages, and your physical memory is divided into what are called as page frames. And like for example, the size of each of these is like, for example, it can be 4 KB or 4 MB. Let's assume it is 4 KB. Yeah, maybe 4 MB is better. Yeah, let's assume it is 4 MB, the size of each page. So what happens is a page of the virtual memory of a process gets mapped to a physical page. So the page that is present here, it is mapped to some physical page. The page that is present here, it is mapped to this physical page. So if you see an address in the address of a variable in the virtual memory layout of a process, it will be something, but the physical address, it could be something else because this got mapped to some other physical location. Are you with me here, roughly speaking, approximately? Virtual memory is stored is mapped to the physical memory. That is where it is stored. Virtual memory is stored in the physical memory. Usually what happens is, if you look at your Chrome browser may not require all the 4 GB of RAM that is there on your machine. Like for example, if you look at Chrome browser, this page may be active in your Chrome browser process is virtual memory layout. So here this one and this one could be active. So if you see, while there is a whole virtual memory layout for a process, out of the whole virtual memory layout, only few pages could be active. Like for example, if you write a hello world program, or if you look at this prime number program, this whole code could possibly fit into one page. So although the whole virtual memory layout, like it is 4 GB is there, you are using only 4 MB. So what you have to do is, only that active page will be allocated a physical page. No, while the passive ones doesn't have anything allocated. The passive pages which are not used, they will not be allocated any memory, because virtual means it's not there. Page is a logical sequence of it's a block of memory. It's a When we say virtual page, it's a or which virtual page or physical page, it's a block of memory. A block of memory, a continuous sequence of bytes. We chunk it and we call it as a block. The program doesn't decide. So depending upon the program, so when you compile your program, depending upon the layout of your program, some pages will be active and some pages will be passive automatically. Like for example, if you see the code, when you compile this prime code, your whole main, which your main, all the instructions, all the of your program, they will fit into one page. So the rest of the pages are automatically inactive. All right. So let's do one small experiment here. So yeah. No, main is present in some page. Main, we cannot say that. The page in which main is present is active. There could be some other things that are present in the same page. So let's say there is something like, wait for a minute. So yeah, it's a virtual memory is our imagination of the process layout. That's true. That's why it is virtual. What do you say virtual reality? It is not there, but no, whatever you are seeing, it is a projection. Anyway, so let's not get there, but let's take a look at this. Okay, let's take a look at this program. Let's take a look at this program. So printf, let me use a global variable. So here I'm declaring, I'm using a global variable here n. That means the variable n is accessible by any function that is present in this program. So let's say I initialize, yeah, I don't do anything actually. Let me keep it like this. All right, so let's compile this program. So GCC pay attention, we are going to do something very fun thing. So enable. So now if you see, there is a variable called n, which is a global variable. It is declared outside. It's called global because it is declared outside the function main. So if you, let's print the address of n. What is the address of n? This is the address of the variable n. Are you with me here so far? What we are doing? Are you all with me? Yes or no? So now if you see here, I am using multiple terminals. This is terminal 0. Now I am creating another terminal, terminal 1. You can see this is terminal 1. So now in terminal 1, I am running this program again, gdb a.out. Sorry. Enable break main, run, print address of it. So if you see, what did you see, notice from here? The program that is running on in terminal 0, when I print the address of the variable n, it got some address. This is the address. This is the address in hexadecimal format. And then if you go and see, this is on terminal 1. This is on terminal 1. So I want you to notice this. I don't know how many of you are able to pay attention. So there are two terminals, 0 and terminal. Right now we are in terminal 1, which if it is in red color, that is active terminal. So terminal 1 is active. Because of that we have we are on terminal 1. So if you go to terminal 0, so that 0 becomes active, it becomes red, right? So if you see, there are two programs running at the same time, and both instances, so the address of the variable n is same in both the cases. So what is happening here? So like for example, if I say set n is equal to 1 and print n, okay, so the value of the variable n is changed. So the variable n is allocated memory at this particular address, We went and changed the contents of the variable n. This is in terminal 0. So now this is in terminal 1. If I print n, the value of n is still equal to 0. Are you all with me? At least are you able to observe what is happening here? How many of you are with me here? Lost? I see complete silence. I'm running two bashes. I'm running two, I am in which terminal? Let's start again. I am in which terminal right now? Terminal 0. What is the address of the variable n in terminal 0? Whatever that, no, 0x555, some blah. Okay, and then I changed the contents of this variable n to 1 by using set n is equal to 1. And when I printed n, it is equal to 1. So now, and if I go to another terminal, and if I print n, the value of n is still equal to 0, in spite of the fact that the address of the variable n is the same. So what is happening here? Tell me. Can someone tell me what is happening here? Anyone? New address is allocated. We have given a value. No. One is a temp value. Main or both, different for both. No, all those things there. It's not. See, this is I think you missed what I was telling here earlier. So on terminal 0, we are running this. We are running a dot out. In terminal 0, we are running a dot out. And in terminal 1, we are running a dot out. We are running. Yeah, someone got it finally. So here, let's say this is the address of the memory location n. This is the address of the memory location n. But the thing is, this is the virtual address. This is what is this address that we are seeing here. This is the virtual address. That's not the physical address. But there is a physical memory. That is what you see in your computer. This is what you buy. So what happens is this gets mapped to something and this gets mapped to something. So initially this is equal to 0, and no, when we made this equal to 1, so this got equal to 1, this got equal to 1, but not this. These two are different. So the physical entities that are allocated to these two virtual placeholders for the variable n from two different processes, they are different. Are you with me here? Are you all with me? Do you understand what is happening? So this is for, it is possible, it's two different, why two different virtual addresses, it's perfectly fine. Physical addresses are different, but virtual addresses are the same. Physical addresses are different, but virtual addresses are the same. So they don't interfere with each other. This process and this process, they don't interfere with each other, because this process is allocated a different set of different memory locations, physical memory locations, and this process is allocated different memory locations. We cannot print the physical address. Good question, Arayma. It's not possible. Why same number as address? It depends on how the compilation happens and loading, linking. There are few other things which determine. But because the virtual address is coming from different processes, Shreyans, there are different. This is totally different thing. We are when we so how what happens when we uh, have two Chrome browsers simultaneously active? Imagine this: if two Chrome browsers are simultaneously active, and if you do something in one Chrome browser, it is going to affect it on the another Chrome browser. Would you be happy? And that's what, because if you see the Chrome browser, let's say in the Chrome browser, uh, in your Chrome browser, there is one particular variable in your Chrome browser, there is a particular variable in which you are storing the URL. So if you see, let's say instead of this, let's say this is a Chrome browser, and instead of a.o, this is Chrome browser. So if this is the address for URL, this is the address where you are storing URL, and this is the place where you are storing URL. So if you change the URL here, if it is going to, and both of them, if this URL and if this URL are allocated the same memory, and if you physical memory, then if any change here in this URL, it is going to affect this, the other Chrome browser. So you don't want that, right? So what you have is every process thinks that the whole memory is available for itself, but internally, the physical memory that is allocated would be different. No, the operating system takes care of this mapping. This mapping of, there is an operating system. No? The operating system, the OS takes care of this mapping. This mapping from here to here, this to here, that virtual to physical memory, it is done by the operating system in a transparent way. We don't need to worry about it. Naimish has this question: if you do the same thing on the terminal twice, would we get the same, would it give the same address? So Naimish, what happens is for global variables, it will be the same, but for local variables, it will be different for a reason. Okay. Yeah, virtual address is decided at compile time for global variables, not for variables on the stack, because the variables, local variables are dynamically allocated. So because of that, the address of local variables, it cannot be determined at compilation time. The address of local variables cannot be determined at compilation time. For global variables, the same address is n. It's not coincidence. But for local variables, you will get a different addresses. No, it is, you cannot access the same physical memory from two different virtual addresses. There is a way to do it, but no, it is a, yeah, it's a kind of advanced idea. Yeah. Good question, Narayan. There is what is called as a shared memory, and so it's a bit advanced idea, so we will not see that. You may study it in your operating systems course. Yes, we can't print physical memory addresses because we don't know where operating system. Uh, it's we Yeah, it's not possible for us to know the physical addresses. What When we print a pointer, you get the virtual address. What do you mean by when we then both will have the same value? Yeah, yeah, that's true. Anyway, so you have a bunch of questions. Hold on to them. Why am I introducing all this? The reason why I'm introducing all this is if we go back to prime function. So this is where. So if you see, this is what I would like you to pay attention, guys. So here, when main calls, so this is the picture that I would like you to understand. So here we have main. So initially when main is active, the memory for the variables associated with every active function, there will be what is called as an activation record that gets created. So in the activation record for main, the memory for the variable I and the memory for variable n will be allocated. This is called as AR, let's call it as AR underscore main. That is AR stands for activation record. Are you with me here? So now when main calls, read and function, when main calls read and function, when main calls read and function. So the activation, this is what is called as a stack. Remember, this is how a whole program memory layout looks like. So you have your operating system somewhere here, you have your BIOS, you have your text or program text means your instructions, you have your data section, and you have your heap, and you have your stack grows here. I'm just drawing this picture, the stack here in a different way. Okay, in a inverted way, I'm drawing the stack so that it becomes easy for you to read. So, and then if you see this readn function, the readn, so this is the activation record for main, which is still present uh, on the stack. And then this is for main. This is AR underscore main. And then there is an activation record for readn. Okay, this is an activation record for readn. Any variables that are local to the read function, the parameters are also local variables for the read function. They will be allocated memory in this activation record. And this allocation of memory to the local variables of a function, it is dynamic. Only when the function becomes active, then only memory will be allocated. And then let's say after we return from readn, so main calls readn, and then so on after line number 41, what happens is the state of the activation record associated with readn will be popped out. Okay, so what happens is after we this is yeah, so this is main. After readn, after we return from readn, so the state of the stack will be again back to this I. And then let's say now main calls prime is prime. When main calls is prime, again the activation record looks like this. So this is the activation record for main, and then this is the activation record for is prime, AR underscore is prime. In the activation record for is prime, like for example, is prime function, it takes a parameter. So the memory for that parameter will be allocated here. So let's say there is this parameter n, and the memory for the parameter is nothing like a local uh, variable. So the memory for it will be allocated on this stack. Are you all with me here? So the address of the variable I, the address of the local variables, they depend on what is the base address of the stack. So if you see this whole thing, this is our whole memory, and our stack starts somewhere here. Our stack starts somewhere here. So the base address, the address of a local variable depends on the base address of the stack. And due to some reasons, what happens is the base address will be different every time you activate a function. So because of that, the base address, since the base address of the stack changes, the address of the local variables keep changing if you invoke the program multiple times. Like for example, let's see here. Let's say here I will have something like int ln. Ln stands for local variables. So let's do one thing. So printf address of n is equal to, let me clear all my drawings. Ah. You can see the global variable remains the same, but the local variable address keeps changing, and these addresses are virtual addresses. The reason why global variable address remains the same is it is allocated memory in the data section, and its virtual address is decided at the compilation time. But the virtual address associated with the local variables, it depends on, it changes at the, it is decided, the memory for the local variables is decided at the runtime as the program is running. So because of that, you can see the local address is kept changing as we are running this program. Are you with me here on this example? Are you all here? Are you with me? Yeah, the local variables are allocated on the fly, dynamically allocated. There is no relationship between virtual address and physical address. Yeah. If the physical address is changed, why should the virtual memory be changed? Array, it's not like this. No, it's the question is your virtual memory is allocated some space. So it is so whenever you want to change the virtual address, the data at a particular virtual memory location, the corresponding physical memory location will be changed. No, we cannot get the value of a global variable after the program gets stopped. The whole memory is deallocated. Yeah, maybe we get the same global. If you compile it again, I think we get the same address. Yeah, that's true. No, the RAM is not divided into many virtual memories. No, not at all like that. RAM is physical memory. That's true. RAM is physical memory. That is because of the compilation process. Okay, because your compiler decided to do it. Okay, so for global variables, the memory is allocated in what is called as a data section. Because of it, it just so happens that the address every time you execute the program, the address of a global variable will be the same. The textbook doesn't have a section on stack. Anyways, so you think about it, you'll understand. We keep revisiting which part of there is a hardware within the processor. There is what is called as a memory management unit. It will do the mapping of the virtual addresses to physical addresses. It's not like that, Lavisha. It's the particular way in which your program is assembled. Because of that, the virtual address for global variables remains the same. No, the address is the same, no, for global variable. Isn't it the same? It's different, huh? Oh, the memory for global variable is also changing. Huh? I thought the memory for global variable should remain the same, more or less. Huh. Interesting. No, no, but after compilation again also, no, because on no, the memory for global variable is also changing actually. If you see here, this one and this one are changing. Interesting. It looks like even global variables will get different addresses. Yeah, so anyway, let's not see. All I want you to understand, unless we dive into how the compilation process works, we don't get all the answers. So what I want you to understand is this. Okay, let's take a step back, and I want you to hold on to your questions, to all your questions. So, what is the first idea? Is the address is the memory that is allocated to different variables in a program. They are virtual addresses and they will be mapped to physical addresses, and we don't need to worry about them, about those physical addresses. Are you with me here at least? The memory that is allocated to, if you look at the address of variables in the memory map of a process, it's a virtual memory map. So if the address that you see of a variable that you see in C program, it is a virtual address, it's not physical address. The mapping of virtual address to physical address is done in a transparent fashion. We don't need to know anything about it. The memory that is allocated to global variable will never be free. After the program ends only, it will become free. Okay. The second idea is there is what is called as a program stack. For every active function in the program, so there is this function. So there is what is called as a program stack. I'll just make it easy for you. There is what is called as a program stack. So so here you have main. So main, so on the program stack, so memory for, so there will be a kind of memory chunk that will be allocated for to hold different variables that are present in the function main. When main calls another function, let's say whatever, no, so fun, so the state of the stack becomes something like this. So this is for fun, and this is for no, this one is still for main. So this is for main. And once we return from once we return from fun, the state, the memory that is allocated to fun, it will be popped out. Are you with me here on this one? On this, are you all with me? This much, are you all with me? Okay. So if you are this much, if you are with me on this, then we are good to go, and maybe look at a few things. Okay, let's now once we return from a function. So this is what we did in the last uh, class also, when we tried to do GDB. When we did a backtrace, the backtrace is showing which frame is present, like right now when we are in uh, so let's look at this program. So this gcc minus g prime func.c, this is the program that we have seen in the last class, gdb a.out. Okay, break main, and we enable run. So what is present on the stack? What is present on the stack, program stack right now? The memory that is associated with, if you see backtrace, the memory that is associated with uh, main will be present. So if you kind of see, if you do info frame, you will get a bunch of information. You don't need to understand all this, but all it says is there is associated with the no, like the activation record associated with main, it will have some information. Okay, and among many things it will store, the important things are, like for example, the local variables I and n will be allocated memory on the activation record associated with main. Are you with me here? So right now we are on line number 41. When we are on line number 41, the activation record on, if you look at the program stack, on the program stack, we have the activation record associated with main. So if you see, there are two important fields. One is I, the other is N. But I would like to say, along with this, some other information will also be present. Let's not worry about it for the time being. Are you with me here this much? This is AR underscore main, activation record associated with me. So now let's do this. Let's do step I. Okay, let me also do one thing. Print address of I. How do I print address of I here? Where are we actually? Optimized dot. Okay, whatever that means. Yeah. So if you look at print address of n, what is the address that you are seeing? Is it a physical address or virtual address? I'll take 5 more minutes and then I'll conclude this lecture. The address that you are seeing, is it a physical address or virtual address? So associated with this virtual address, there will be a physical address. Yes or no? And that physical address we don't know. And it can keep changing also actually. For I would like to say, the physical address associated with, no, with this, it could keep changing also. It is quite possible. So, but we don't know the physical address associated with the variable then. So now what we are doing is we are stepping into the function readn. What will be the state of the program stack? If you do BT, you can see that the program stack contains the activation frame associated with readn, followed by below that there is an activation. So this is the stack. Okay, this is the stack. On the top of the stack, you have the memory associated with the. So this got transformed into this. This got transformed into this. Okay, so this is the AR. This is the activation record associated with main. It just remains the same. And then on the top of that, we have the activation record associated with readn. And if you see, n is a local variable here. So the memory for n will be allocated here. This is n. This is the activation record associated with the readn. And what I would like to point out here is, the end here, and the end here, they are different. Are you with me here? Are you all with me here? This is some other stuff. The end here and the end here, they are different. This is very important observation. All right. So now let's get going here. So you can see BT info. I'm just trying to see if I can get more information from here. Yeah. So now can you see BT full command? This is what I am looking for. Are you with me here, guys? This isn't nice that this is the activation frame. This is the activation frame. I want you to pay attention here. This is the activation frame associated with main, and this is the activation frame associated with readn. Are you all with me on this one? And the value, the n here and the n here, they are different. If you understand this, I will be very happy for today's lecture. Good enough. Let's keep going. So we know there is an interesting question. So why isn't I having any address? So my guess is what happened is I is allocated. I is not used in main. So because of that, the compiler didn't allocate any memory for it. If you go back here, I is not used at all in the program, right? The compiler recognized that we are not using I. So it is saying it is optimized out. Optimized out means the compiler thought there is no point in allocating memory for I because I is not used at all. So because of that, it is saying no, I is optimized out. There is no address for the variable. Does it make sense? You understood? Yeah, we can try it. So we'll do it later. No, it's not like that. It's not used at all, Pradham. If you in main, the variable I is not at all used. The compiler thinks what's the point in allocating memory for it at all. So it didn't allocate any memory to it. Okay. So now let's get going. So now, uh, so where are we? So we are control L. Yeah. So this is next. So now we are out of, so we are in read. So we do next, next. Let's say I enter some value 12, control L. Okay. So now we will do beautiful. So now when we do beautiful, what are we seeing on the screen? You are seeing only the activation record associated with main only. Does it make sense? Again, are you with me? You are able to see, right, that now since we are out of read, it is not there. So now let's go inside next type. So, or next step 5 it should be. Yeah. So now if you do BT, you will see this again. That main is there, and then is prime is on the top, and since n is a parameter, so let me use this BT full. This is what we have. Okay. Yeah. So come here, and then again we do BT full. You will see this. That's it. You understood summary of today's lecture. I want you to understand this thing, like how this idea of program stack, because it sets up many things. Because when we do recursion, that's what we will do in the next class. When we try to write recursive functions, every active function will get its own memory on the stack. Since var from main is present, can we access it in? We can access it, Arush, but in a very convoluted fashion. You use GCC minus O0. Like, that's a way to do that. Okay. You're all good today. It's so. What are the two main ideas? Can someone summarize two main ideas that you have that we have learned today? One is program stack. What is the second idea? Yeah, virtual memory. The idea virtual memory and program stack. Virtual memory to physical memory mapping and program stack. These are the two important ideas that we have learned in today's class. With these two ideas, you will know your understanding about how programs work. If this any problems in your program, so many ideas becomes very, very clear when you work with programming problems. All right. So I will stop here, and we will catch up on Saturday. On Saturday, we will solve some interesting problems. And I want to give one challenge problem before we leave. Maybe I should give it on, I will give it on Saturday. There's one interesting challenge problem that I would like to give. I will take it up on. Okay, we'll catch up. We'll catch up on Saturday, and we will take that up. All right. Okay, then let's